Hello and welcome to Noel's Retro Lab. Today we have these two Commodore 64s that we need to repair. We didn't get around to doing it last time because the repair of number one took a lot longer than I expected, but hopefully today we can tackle both of them and fix them. If you haven't watched that video, I recommend you do that now because we're going to be using a lot of what we learned then to repair these two. So let's open them up and find out what's wrong with them. So first things first, a quick visual inspection of the board, and everything looks pretty good. I don't see anything obviously wrong. I don't see any modifications, no signs of anybody messing around with things. So yeah, hopefully we're the first ones doing anything here. And let's start by checking some voltages. So first of all, make sure that we are getting 5 volts. Yep. And 5 volts good to the LED. Yes. That's good. Now let's check these voltage regulators. Input is 10. Output is 5. Yeah, that's fine. And this one, input. Yep. And output should be 12. Yes. Okay. Let's check in on the other side of the board, as far away as possible. So we should have 5 volts in here. It's a little low, but it's probably fine. And then about 9 AC here. Yep. Let's make sure the VIC is powered up correctly. Should have 5 volts in pin 40. And we do. And we should have 12 in pin 13. Yep. Okay, that looks good. This has been on for a few minutes, so we can quickly check for anything getting particularly hot. Hotter than usual. I don't see anything. The ROMs are maybe a little warmer than they should be, but usually what I'm looking for is something that is difficult to leave your finger on. That means, yeah, okay, there's a good short in there. These are actually really cold. Let's check for a clock signal. Some of you have said that you don't have access to an oscilloscope, which is, is very handy, but a lot of times you can do a lot of measurements with just a plain multimeter. And this is one of those cases we just want to make sure that the clock line is not completely low. Clock in is 1, and so 3.6, yeah, that's probably about right. This half the time is up, half the time is down. You could even check clock out, 39. That should also have some activity. Yep, it's pretty high, it's pretty close to 5, but yeah, that's probably fine. And hey, while we're at it, let's check the reset line of the CPU just in case. So this currently should be high because reset is active low. So this should be close to 5 volts. Yeah, okay. So at least we don't have the same problem as we did last time. Moving on to the next test, let's check out the dead test cartridge. Everything is plugged in. We turn it on. And remember, it should stay blank for a few seconds, but I'm already noticing something. When we turn on the power, even though the screen remains blank for a little while, the TV should receive a signal. But right now it's not receiving any signal that it can make sense out of. That's why it keeps saying no signal and showing that message. So that means we are not sending in a signal at all for video, at least not a reasonable signal. That could mean the VIC chip is completely bad. We know it's powered, so at least it has that. And we know the clock signal is working, but it's not sending any video signal. So we should definitely check that out with the oscilloscope. So let's check the color and sync signals on the VIC, which were 14 and 15. 15 is the sync signal. That is definitely not right. And color, these are not right at all. This probably means the VIC chip is bad. So just out of curiosity, remember that I had a look at the clock out of the CPU, and it seemed higher than it should have been. So let's just have a look at it. I want to see what kind of signal it is. Yeah, it was 39. Oh, and it's flat. Well, that's a surprise. What it's clock in then? Clock in is in 1. Oh, wow. So I totally didn't plan this, but this is a perfect example why you really should rely on the oscilloscope. The multimeter told us that clock in was about 3 volts, and we said, yeah, on average, maybe that's right. But it turns out there is no signal there. Okay, let's backtrack. The clock signal should go through the VIC. So it gets generated here in this crystal oscillator. It goes through some logic there to generate the oscillation and to generate a better wave signal. So the clock signal gets fed into the VIC in pin 22. That seems okay. $11 MHz? That seems a little high. And pin 21 should have the clock for the color signal, which should be 17 MHz. And yep, there you go. Exactly 17 MHz. So I pulled up the schematics for the clock circuit, and it's actually pretty complex. It involves all those chips. I'm not really sure why it needs to be that complex. Maybe because there's the PAL NTSC selection, but still, this is by far the most complex clock generation circuitry that I've seen in any computer. So one weird thing is that the clock circuitry generates a clock signal that is fed into the VIC chip. And then the VIC chip generates a CPU clock signal. So far, so good. That's pretty normal. But then the weird thing is that that clock signal is then fed back into the clock circuitry generation. So maybe if the VIC chip is defective, then that could throw off that signal. I don't know. So since this is socketed and is really easy to test, let's take it out and put it on a working board and test it out. All right, so let's try the VIC chip that we pulled from the other board on this one that we know is working. So we put it in. The nice thing about these chips is that they're socketed, so it makes this check very, very simple. So we turn it on, and yeah, this one seems to work just fine. Okay, so that's good. We know the VIC chip is working. There must be something wrong in the clock circuitry. Let's go check it out. Okay, so let's check the origins of the clock signal, see if we can figure out where it goes wrong. So it starts here in the crystal oscilloscope, and we should see a very small ripple here. And let's do an AC like that. So it's hard to tell with this oscilloscope. It's not picking up the exact frequency, but I'm going to say that looks about right. It's very zoomed in. It's 200 nanoseconds. So that's probably good. The output of the crystal oscilloscope, that signal gets fed, first of all, into U31, and this generates the clock signal for the, what is called like the dot color, is probably used for some video generation. And it says for a PAL system is 17.7 megahertz. And that's in pin 10. And let's see if we can get up. There we go. We get 17.7 megahertz. So that's exactly right. So far so good. Then this goes into U30, which is this one. And in pin 6, it generates, I think it was a 1 megahertz signal. There we go. And right, no, 2 megahertz. That's right, 2 megahertz. And then it gets split up into two signals of 1 megahertz. And the output is U29, output 9. And there you go. That's the 1 megahertz clock signal. So far so good. And then when we feed back the CPU clock back into here, so this is in U32. So the signal that we just saw gets fed in pin 1. So that should be a 1 megahertz signal. Yep. And then in pin 3, we do the CPU clock, and this was flat. Oh, so wait. We're getting a CPU clock signal. Check it at the CPU itself. Was pin 1. That was an easy one. Wow. We're getting a correct. And what about the output clock in 39? Wow. So this seems to be, the clock signals seem to be working correctly now. But they weren't working a second ago. This is the same board. There's one difference though. I pulled out the VIC chip, tried it in the other board, and put it back in. That's something I didn't mention before, but sometimes socketed chips are not making good contact. Maybe they've been sitting there for a long time and they get a little rusty or whatever. And then this is why it's recommended to any chips that are socketed to take them out, look at them just to see if there's any corrosion or anything, and then put them back in. That's often enough to make sure that it makes good contact again. So it looks like we're getting correct clock signal here after all. Let's check out the display again, just in case it's already working. Okay, let's run the test. This time I'm going to do it with the cartridge in, just in case. Oh, notice as soon as I turned it on, the no signal message went away. So it's definitely an improvement over what we had before. It's still normal, not getting any video, any image, but we should have gotten something by now. So it looks that even though we fixed one of the problems that we had on the board, it looks like we still have a black screen. And we also know that because this is happening with the cartridge, we're back to, well, we know this is not the VIC chip. So really we're back to the CPU or the PLA. And the PLA is the number one suspect when that happens. If it's not either one of those, it could be some other chip related to those two systems. But I'm going to do a quick inspection of the signals and then probably replace the PLA and try it on the other system. So the PLA, it's like a big logic table, and given certain inputs, it always puts the same outputs. So let's just look at those outputs and make sure we have reasonable signals around there. The outputs are from pins 10 through 18. That's nothing. That's nothing. So the outputs look to be constant. That's pretty odd. What about the input itself? So some of the input pins. Oh. Are we getting any? Are we back to having no clock? No, we have a clock. Yeah. So some of the inputs are bits on the address bus. So yeah, 2, 3, 4, 5, 2. Okay, there's nothing on the address bus. Let's look at the address bus directly on the CPU. Right there. Yeah, there's no signals on the address bus. That is really weird. The reset line is fine, right? Yeah, the reset line is fine. So I'm saying this is really weird because I would expect the CPU to be generating addresses for refresh of the dynamic RAM. What about the data bus? Data bus is 30 through 37. Okay, so there is some activity in the data bus. That's a little weird. That's fine. Some are a little weird. And some look fine. But definitely no addresses in the address bus is really weird. Something else that should be writing to the address bus is the VIC chip. Apart from generating the video, it also takes care of refreshing some of the DRAM. We'll generate some of those addresses, 24, 25, 26. Yeah, like that. So there is activity there. Those addresses go through U26, which is this one, and they get added to the address bus, or at least to the lower 8 bits of the address bus. So for example, 2 is an input. There's nothing there. 7. So 7, there's some activity there. And 6 should be the output. Nothing. And this is controlled through pin 1. Oh. Okay, this is really wrong. Pin 1 is AEC, which is address, I believe it stands for address enable control. And it's a signal that the VIC generates when it needs to take over the address bus. Wow, and here it looks totally fine. Let's do a quick check, but I'm thinking it's the same problem that we had before. The socket is just not making good contact. So, by putting it back in, now the clock signal is working, but there are some other pins that are not working. And yeah, if the CPU thinks that the address enable control is on all the time, then it's not going to be doing anything. So AEC on the VIC chip is connected to the output enable of U26. So when the VIC chip needs to put some addresses in the bus, it turns that on and they get added to the address bus. So let's check. 16 here should be connected to pin 1, and it's not. So we could have a broken trace, or it could be the socket. Let's try the socket. All right, this is a little cumbersome, but let's try doing it this way. So let's start with 20. Okay. 19, yeah. 18, 17, 16, there is no contact. And 15, yeah. So 16 is not making any contact from the pin and the VIC because we saw there's the correct activity. It's just not being sent to the rest of the board. So given that, and given that we had problems with this before, I could try taking it out and cleaning it, but I'm more comfortable changing the socket completely. And at the same time, I'll remove this shield because it's pretty annoying. This socket is pretty horrible. It looks like it only makes contact on the inside and not the outside. So as soon as those little metal tabs get pushed in a little bit, it stops making reliable contact. So we should definitely replace it. So there you can see how there's only a single side, this metal only on a single side. And here's the new one that we're going to put in. And it has metal on both sides, so this should make a much better contact. we can do the same test as we did before and check if we have continuity between pin 16 here and pin 1 in U26. And there we go. Let's see if it works. No, we still get a blank screen. But I suspect that if we look at the signals now, we should be seeing normal activity in the address bus. Let's check that out. All right, so I have another theory, and that is that maybe the voltage that we read early on the 5-volt line is actually not enough. I was just reading how the 6510 really needs 4.75 volts to operate correctly, and it looks like we're more around 4.68, 4.69. So that could explain some of the lack of signals around the CPU. The 5 volts at the input are fine. I've measured them there. There's pretty much spot on 5 volts. So what could be causing that? Normally that would be caused by a short somewhere in the board. Just in case, I've removed the SID chip. And what I did is I turned the board on and I've left it sitting here for about 5 minutes just to see if anything gets overly warm. And it looks like some of the ROMs are a little warm. So I'm using this like laser measuring gun. So just for comparison, the CPU sits at about 2930. This ROM, 28, but check out this one. It's like 30, 37, 38. That seems way too warm. Same thing with that one. Even the PLA doesn't get that warm. 27. So maybe we should desolder those two and then see if the voltage of the board changes with those two ROMs removed. Okay, now with the ROMs removed, let's check the voltage on the CPU. 4.7, yeah, that's a lot better. So let's give this a try and see if it works now. So I tried it and still a black screen. So I want to have a closer look at the signals around the CPU. In particular, I'm going to be looking at 2 and 3. Before those were all steady. And we still have 2, which is ready, is high, IRQ is high. That doesn't seem right. Read write is 38. There's also no activity there. It's held high. So those don't seem right. Looking at the address bus now, it looks pretty good. So we've made some progress. They look fine. They look rather similar. Oh, and then it's high. So we have a few bits that are stuck on high for the data bus. And then that one looks pretty bad. That's almost like somebody's driving this up and down and there's a short and it's going to 5 volts. That doesn't look too good. Data bus, on the other hand, yes. Oh, there's activity. Not pretty, but there's activity. I mean, if it's trying to read from the ROMs right now. So given that, especially given bit 15 of the address bus, maybe there's still a short somewhere to 5 volts. Some of the potential things could be the other ROM chip, even though it doesn't get hot. The PLA is still doing nothing, but the inputs are steady, so it's not supposed to do anything. I suppose it could be shorting those address lines. I mean, those that are held high and low are coincidentally the ones that are going there, but I would expect it to get hotter, so I'm not convinced that that's the problem. But at this point, it's definitely worth taking those two out and testing them separately and going from there. All right, I removed the extra ROM and the PLA, And before I even try them, I like to run some tests just because I like to understand what's going on. It's not just a matter of swapping out chips until something works, but I want to know why. And that also helps a lot to learn for the future. So what I want to check now is, does our voltage change at all? Last measurement we had done was 3.7, I believe, 3.75, which was borderline okay. And now if we measure it again, we get 3.86, which is much better. So I think there was definitely a short somewhere in there. Let's see if we get the same thing here. Yeah. The other test I want to do is whether A15 is still being sort of fought over being high and low, having that ripple. So A15, okay, A15 is high all the time. At least there isn't. So that ripple must have come either from the PLA or the ROM. We can put them back to find out. So let's do that. Okay, I put the ROM back just to eliminate candidates, and A15 doesn't have the ripple. So it's probably coming from the PLA. Great. Let's test the PLA on the other board and see what happens. Okay, here's the working board with the PLA that we suspect is bad. So let's turn it on and see what happens. And nothing. So we get a black screen. So we know for sure the PLA is bad. There may be something else going on the other board. There seem to be multiple things, but at least we know that's wrong. So now we can put this PLA, the one that worked in here, and try it on the other board and see if we can make it work or if there's something else. So we're back on the board that we are working on, and we have the PLA that we know works. We don't have the ROMs or the SID chip, and that's fine because we're going to be using the dead test cartridge. So if all those three chips work and the sort of helper systems, then we should be able to get the screen with the tests. So let's find out. Oh, there we go. It gave me a little scare because it took longer than I expected. Yep, so we are getting the test. At least we have basic functionality going on in here. I'm pretty sure the ROMs are bad because they were overheating so much, so those we're going to test separately. Let's add the SID chip and see if everything still works fine. Yep, so it's at least not preventing it from starting up the tests. So really, we're down to the ROMs themselves. It turns out I had another Commodore 64 with the ROMs already socketed. So I popped them out and I put them in to try. We also have the SID chip installed. And with all of that, boom, we have a working Commodore 64. So not only that, but I did a little bit more digging and testing things out. And the first ROM that we removed, which is the basic ROM, that one is actually working okay. So the only faulty ROM was the kernel ROM, which is this one. That's the one that was getting the hottest. So to recap, the problems with this particular board were, first of all, the socket on the VIC chip that it was preventing signals from reaching the rest of the board. We had one bad ROM and we had a bad PLA. That's quite a lot. And this is actually a perfect example of why I always suggest testing out individual ICs on a working board and not the other way around. Because if we had taken a PLA that works and popped it in here, we would have still gotten a black screen. That would not have helped at all. They would not have told us anything. So I think this was a pretty good example. This is the failing kernel ROM. So how do we go about replacing it? Normally with a ROM, it's not a big deal. You just get an equivalent EPROM and burn it in a programmer, EPROM programmer, and pop it in. All done. Well, this is not so simple. Notice the difference? 24 pin, 28 pin. It turns out most EPROMs, the 27 whatever size, they are typically 28 pins, whereas these ROMs, these Commodore ROMs, are 24 pins and they are 8K. But the signals getting to them are pretty much the same. This just has a few extra pins. So we'll need an adapter that makes this fit into this. Well, not into this, but where this fits. There's one added restriction, which is, if you remember, the Commodore ROMs were all next to each other, pretty tightly packed. Our adapter can't extend sideways because it's going to bump into the other ROMs and the other chips. So it needs to be pretty compact. How are we going to do that? With a 28-pin socket, some pins, and then we are going to add a few bridges to send the signals to the right place. Let's go ahead and try that. All right, here's the final adapter. It's not the cleanest job ever, but the materials weren't quite right. I wish I had a different kind of adapter. But at least you see there's just a few connections, and then the rest of the pins are the same. So let's go ahead, burn the EPROM, and test it out on the board. So what I've made is I've created a ROM that is 16K, which is the size of the EPROM chip that we're going to burn it to. I didn't have any 8K ones. So it's just the kernel ROM repeated twice. So it doesn't matter whether we address it on the low half or the upper half, we're going to get the same data. We'll pop in the EPROM, and we burn it. Okay, let's see if that worked. All right, so there's our contraption on the board. It's kind of stacked up, but I think there's plenty of room inside the C64 case, especially because I don't keep that shield protector. It's absolutely not needed anymore. So let's turn it on and see if that works. Let's see. And there we go. We have a working Commodore 64 with our custom EPROM adapter. Excellent. So that took a while to repair this. It was a lot more effort than I expected. It didn't help that there were 3 things wrong with it, not just one. So yeah, it took longer to diagnose and fix. Anyway, I thought it was interesting, and I hope you liked that video. If so, please give it a thumbs up. And if you want to know when I release the video for the next Commodore 64 repair, hit that subscribe button right over there. See you next time.